All right, section 2.3 here is on continuity and end behavior. Okay, so we're going to be talking a lot about, or I guess often about, is a function continuous or is it not? And if it's continuous, that means that there are no breaks or holes in the graph. Okay, so this is an example over here of a continuous function. You can see that if I trace this along, it's all smooth. There's no breaks or holes or anything to make it not continuous. If there are breaks or holes, we call it discontinuous. Okay, so that's pretty straightforward. Types of discontinuity that we're going to look at, there are 3 types. The first one is called infinite. Okay, and when we have an infinite discontinuity, if f of x increases or decreases infinitely as x approaches a from the left or the right. Okay, so that is kind of some weird language here. So we're looking at this x equals a, so we can think of it as this vertical line here. Okay, so as x approaches a from the left, okay, it says from the left or the right, but if we look at as x approaches a, so we're coming from this direction, what is our y, our f of x, our y values doing? And they're going down here, right? We see this, they're going to start going down. And we talked about this, so there's an asymptote here at x equals a, and so they're going to get closer and closer and closer and closer and closer to a, but they're never going to touch it. Okay, and you can see that the function here has 2 legs, this one on the left side and this one on the right side. And from the right side, your y values are going up to infinity as the graph approaches a from the left here. Okay, so I'm just going to erase all this really quickly. And then I'm going to read this definition again. So you have an infinite discontinuity when f of x, so we're talking about y values, increases or decreases infinitely. We're either going to positive or negative infinity as x approaches x equals a from the left or the right. So again, as if we're on the x-axis going this way or this way, if our f of x, our y values are going to either positive infinity or negative infinity, then we have an infinite discontinuity there. All right, and the second type is called a jump discontinuity. Okay, so that is when f of x, so we're talking about y values, jumps from one point to another. So you can see here, we have this line here, and then all of a sudden we have this hole. So it's not defined here at x equals a in this negative, but it's actually defined up here at x equals a, and then the graph continues on here. So jump discontinuities are a little bit easier to understand. Basically, you have this huge break, and the graph jumps from whatever this negative value is up to this positive value. It doesn't have to be from negative or positive, it just has to be any kind of a jump where there's a break in the function and it continues on in a different spot. So you'll most often see a hole here, and then like a hole as in like an undefined value, and then the actual value that the function's defined at is just at a completely different spot there. Okay, so that's a jump discontinuity. And the last one here is called a removable discontinuity. Okay, and these are just holes. You have a function that looks normal everywhere, but this one place we have a hole. And again, this doesn't really seem like a situation you're going to come across often, but there is actually, we'll actually be working with functions that are like this as well. So the definition says here, when f of x is continuous everywhere except for a hole at x equals a. So holes are considered removable discontinuities. Okay, Examples. So our directions here are to determine whether the function is continuous, and if not, identify the type and location of discontinuity. Okay, and I just want to make a point over here. If we're asked for location, okay, so this one just straight up says give the location, but if you're also asked like where does something occur at, right, that's the location, you're always going to be given x values. Okay, so at x equals a, there's a discontinuity. At x equals a, there's an asymptote or whatever. Okay, so we're looking, if they say, where does this occur, you're always going to be given the x value of that spot. Okay, so let's look at number 1. So we asked ourselves, is this continuous? Are there any breaks or holes in the function? And you can see here that there is a break. We move from this leg here, and it jumps down to here and continues the function on in a different spot where it's not smooth and it's not continuous. Okay, so we have a jump discontinuity. I'm just going to abbreviate there. At, let's see, x equals 1, 2, 3, 4, 5. At x equals -5. All right, so moving on to number 2. So does this function have any breaks or holes? And I remember my teacher in high school said, can you put your finger on one spot and trace the entire function without lifting up your finger everywhere that it's defined? And in this case, the answer is yes. So we'll say that this is continuous. There are no breaks or jumps. Continuous, that looks weird. There are no breaks or jumps in this function here. Looking at number 3, it looks like we have 2 different sides or legs of this function here, this one up here and this one down here. So I think we would consider this probably a break here. And we're asked what kind of discontinuity this is. So it looks like we are dealing with an asymptote here at x equals 1. Okay, and as we approach x equals 1 from the left, we're going to positive infinity. Our y values are going to positive infinity. And as we come from the right, our y values are going to negative infinity. Okay, so that means that we have an infinite discontinuity here. So we'll say infinite. I'm supposed to be in purple. Infinite discontinuity at x equals positive 1. That's where that vertical asymptote is. All right, number 4 here, is this continuous? Can I place my finger in one spot and trace it all the way down without lifting it up? And the answer is yes, this is continuous. There are no breaks or jumps here. Number 5, there's a blaring hole right here, so we know that automatically if there's a hole, it is not continuous, and we call holes removable. Discontinuity is removable. I don't think there's an E in there. Discontinuity. This is at x equals 1, 2, 3, -3. Okay, again, we're giving x values for location. Okay, here it looks like we have 2 legs of this function, which means we have an infinite discontinuity here. We have an asymptote at x is equal to 2. And we also have this hole here at x is equal to 4. So in this case, we have 2 reasons why this function is not continuous, and we will include both of them. So we'll look at the asymptote first. That is an infinite discontinuity. Okay, and this occurs at x equals 2. And then the hole, we have a removable discontinuity at x is equal to 4. All right, and that's all for continuity. Let's move on here to end behavior. Okay, so end behavior, let's read this box here. As x moves towards positive infinity, and negative infinity, end behavior describes what is happening to the value of x. Okay, describe the end behavior of the graph to the right. Okay, so first we're going to look at as x goes to infinity. Okay, so as x goes to infinity, what is happening to f of x? What is happening to the y values? Okay, so let's look over here. We're looking at as x goes to infinity, we're going this way. Okay, what is happening? We are decreasing and we're decreasing and we're decreasing, okay? So as x is going to infinity, as we're moving to the right, we're looking at the very right-hand side of this function. Our x values, our f of x values, our y values are going down to negative infinity. Okay, so as x approaches infinity, that's what this means. As x approaches infinity, f of x approaches negative infinity. Okay, and then we'll look at this from the other side as x approaches negative infinity. So as our x values get smaller, what are our y values doing? Well, they're getting bigger and they're getting bigger and they're getting bigger right here, right? So as x continues to get smaller, y will continue to get bigger. So as x approaches negative infinity, f of x approaches positive infinity. Okay, so let's look at the end behavior of these graphs here. So describe the end behavior of each graph. So as the way that we write these, they're always going to be in these statements like right here. Okay, so we should always start with, and I should switch back to purple. As x approaches, I always like to start from the left. As x approaches negative infinity, f of x approaches, okay, what are we going to put here? So we're looking at as x gets smaller and smaller and smaller, it looks like f of x is getting bigger and bigger and bigger in that direction. So as x approaches negative infinity, f of x approaches positive infinity. Okay, and then as x approaches infinity, so we're going to be looking at this right side, it looks like f of x is also going up. So on both sides, f of x is approaching infinity, and you can see that, let's erase some of this. You can see that here on the graph, that on both ends, the very right side and the very left side, these arrows are pointing up. So that means in both directions, as we go to negative infinity and as we go to positive infinity, our y values are going to continue to get bigger and bigger. Okay. Number 8 here, as x approaches negative infinity, f of x is doing what? Well, it looks like as we go down to negative infinity, we're looking at this side here, and our arrow is going down, so f of x is going to negative infinity. And as x approaches infinity, so we're looking at from the right side, we want to look at the right end here. Our arrow is also pointing down, so we are going to negative infinity in both cases. Number 9 here. Okay, so as x approaches negative infinity, so we're looking at the left side here. You see two arrows that are going down here, but if we look at smaller and smaller x's, we're actually going to be paying attention to this one, even though they're both going down. F of x is going to be approaching negative infinity. And as x approaches infinity, we'll look at the rightmost side of this, which is this arrow. F of x is approaching infinity. Okay. Let's look at, so this is just, these functions are either going to infinity or negative infinity, but it's not always going to be infinity or negative infinity. You will have cases where f of x is actually approaching a number, and that's when we have these horizontal asymptotes, okay? So as x moves towards positive infinity, and negative infinity, it is possible for f of x to be approaching a certain value. Okay, so let's look at the graph over here. Okay, so if we're looking at as x approaches negative infinity, so we're looking at this arrow here. This arrow is not pointing up or down. Okay, and we can tell by our last section when we talked about asymptotes, that it looks like there's an asymptote here at y is equal to -1, right? You can see it on both sides. So that means that this is getting closer and closer and closer to -1, but it's never going to touch or cross. But as we get smaller, our y values, instead of going up or down, they're actually just going to be getting closer to this asymptote here. Okay, so as x approaches -infinity, so I'm jumping down to the second one here. As x approaches -infinity, f of x is actually going to be approaching -1. Okay, so it's just going to get closer and closer and closer and closer to this asymptote. And that's really the only direction that it has. It's just going to get closer to this one value. It's never going to go to -infinity or positive infinity. It's just going to get as close as it can to -1 forever. Okay, so if we look at it from the right, as x approaches infinity, we have the same kind of thing going on. We have an arrow here, so that means we're getting closer and closer and closer to -1, and that's the only thing it's doing. It's only ever just going to get closer to -1. It's not going to do any other kind of behavior. So as x approaches infinity, f of x is also going to be approaching -1. Okay. All right, so let's take a look at these last 6 examples. Number 10, as x approaches -infinity, going this way, it looks like there's a horizontal asymptote here on the axis, so at y equals 0. And it looks like we're just going to, y is just going to get closer and closer to 0. So we say f of x is going to be approaching 0. And as x gets bigger, as it approaches infinity, the same thing, f of x is going to be, this is supposed to be 0. F of x is also approaching 0 from this side. It's only just going to keep getting closer and closer and closer to 0. All right, number 11. Okay, so let's identify if we have an asymptote. It looks like we have one right here at -3. And you can see on both sides, these are just going to get closer and closer to -3. So from both sides, our f of x is just going to get closer to -3. So as x approaches -infinity, f of x is approaching -3. And the same thing for the other direction. As it gets bigger, f of x is just going to get closer to -3. For 12, looks like we have another asymptote here at y is equal to 2. Okay, so from both sides, they're just going to continue to get closer to 2. So as x approaches -infinity, f of x is approaching 2, and as x approaches infinity, f of x is approaching 2 as well. All right, so we will see times where these aren't always going to be the same, but for these horizontal asymptotes, a lot of the times they are going to be the same, kind of by definition. Okay, so we have a horizontal asymptote here at y is equal to -2. It looks like our end behavior, we're just going to keep approaching -2 here, which makes it pretty easy. So as x approaches -infinity, f of x is approaching -2, and as x approaches infinity, f of x approaches -2 as well. For 14, you can clearly see there's an asymptote at the x-axis at y equals 0, and in both directions we're just getting closer and closer to that. So as x approaches -infinity, f of x is approaching 0, and as x approaches positive infinity, we're doing the same thing. We're just getting closer to 0 there. Number 15. Okay, so we have a horizontal asymptote here at -1, 2, 3, 4, 5. Okay, but we only have one function here. Okay, so this function is continuous. It's just got one kind of big section here. So we do have to continue to look at it from both sides. So as x approaches -infinity, what is f of x doing? Okay, where is f of x going? So as our x's get smaller and smaller and smaller, it looks like our y values are just shooting up. Okay, so because of this arrow here, f of x is going to infinity as x goes to -infinity. And as x goes to positive infinity, what is f of x doing here? So let's look at the other side. As x is getting smaller and smaller and smaller, it looks like we're getting closer and closer and closer to -5 here. So as x approaches infinity, f of x is going to be approaching -5. Okay, so there's an example where they're not the same. And that is continuity and end behavior.